Yeah, hello, Fred. Hello to everybody. And thank you for joining this webinar. This is about learning and applying reliability with generative AI. So we were talking a lot about this topic with Fred and the other hosts of Chain Reliability. And I would like to show what is my experience on that, and discuss potential also application with you. So I have divided the agenda in 4 points. So we first get into the introduction, and then we move to the theory of accelerated lifetime modeling. And in particular, we will focus on avoiding pitfalls that are included in this approach, because then we want to create a web app on accelerated lifetime modeling with the support of generative AI and Python. But as I said, for creating the app, we need to have a solid background. So therefore, I will illustrate what are the most relevant and famous pitfalls we encounter when applying accelerated lifetime modeling. And after doing that, we wrap up and we discuss the conclusions. So as I said, we were discussing with Fred and the other host about the use of AI. And basically, AI has become a sort of learning amplifier, okay? And that can be used for learning and applying reliability engineering in a really effective and productive way. It's like a sort of booster for productivity. And I was thinking about what are the learning amplifier we are using as professionals. So I'm not expecting that everybody dealing with reliability engineering has a PhD on reliability. There are a lot of people that are interested in the reliability engineering, and they are requested to do that. And as you know, Agenda Reliability is offering a lot of trainings and a lot of great documents, literature, and that. And you might found all the other amplifier in the Agenda Reliability, like videos, webinars. You might want to apply some use some software, some apps. You probably, if you are professional in the companies, you have some templates, some checklist, and you join some communities, as I do, for example, with the Chain Reliability for exchanging, with the aim of exchanging about reliability topics. Yeah, but on top of that, I put AI assistants. Yeah, and then I compare these learning amplifiers. Considering some criteria like learning speed, practice support, dev support, judgment support, validation, scalability. And it turns out that this is my personal rating, but AI assistants are really increasing the speed in how people learn reliability. They can support a lot in terms of practice, because with AI you can generate apps, and apps are interactive, and therefore you can create scenarios. And testing scenario is really effective because you don't read just something on the book, you can practice it, okay? The level of dev is dependent on the level of the prompt. Yeah, if you are a new reliability engineer, probably you do not have you cannot say interrogate the AI tool same as a good reliability expert. Therefore, the dev support depends on how you prompt your question and you conversate with the AI tool. And where the AI is not really good, to my opinion, is about judgment support and validation support. Yeah, when compared, for example, with communities peer discussions, because AI is supporting in exploring concept, in creating scenarios, but of course it cannot be used for evaluate a concept, or it cannot take over any responsibility. that should belong to the expert, the engineer. So in terms of judgment and validation support, yeah, it should not be used as an evaluator. In terms of scalability, is really effective because with creation of the web apps and dedicating Python scripts, you can really you can create much better tools when compared to Excel, for example, what is really widespread inside the organizations, right? And yeah, what I want to propose you to do in this webinar follows these 4 points. So basically, we will be using generative AI tool, in this case ChatGPT, and we are combining them with theoretical knowledge that should be the pillar of the reliability engineer. And then what we can do is to let the AI tool to translate the question into code, and that is the Python part here. And then we can make this Python code interactive with Streamlit. There's another free tool available in the internet. And in this way, you are going to create a really powerful app that you can use for learning reliability. Okay, so we are not discussing in this webinar how to develop new concept, how to explore new concept thanks to the AI tool. We are let's say at the basic level, yeah, how we can learn more effectively thanks to AI tools. Great. So what AI can do, right? What AI can do, it can explain concepts quickly. It can generate practical example. I already said it. It can compare methods, create exercises and quizzes, support coding and simulations, structured thinking, help communicate reliability and challenge assumption. These are main points that AI can do, right? And in order to do that in a proper way, you need to develop some skills in conversating, yeah, because the AI response they become better when you force the AI tool to deep reasoning, to do advanced statistical methods, and so on. Okay, so if the question is naive, the answer will be naive as well. So basically, as for all the other models, yeah, garbage in, garbage out. This principle applies also for AI. What AI can do, I have already said it at the beginning. It cannot guarantee correctness, and it cannot validate physical reality by itself, and cannot replace expert judgment, cannot own engineering responsibility, cannot know whether if evidence is sufficient, cannot replace standard validity procedure, cannot detect all hallucinations. So there are some hallucination that depends, of course, on the way you are prompting. But I would say if you take care about how you formulate the assumption, yeah, you probably get good results. If the assumptions are not correct, if the assumptions are wrong, so basically all the process will be wrong, yeah. And I can tell you a story. I was asking ChatGPT why was some leakage in the bathroom, and basically I was expecting, since the leakage was coming from the floor, I was expecting was something big, and so basically the ChatGPT suggests me to do a lot of let's say investigation, probably also breaking the floor in order to see where is the leakage. But it turned out that the leakage was about a tube that was fixed, was not screwed properly by myself. But since the assumption was wrong, all the procedure that ChatGPT was suggesting me was basically wrong. So I think if you spend time in the definition of the correct assumption, and you provide enough boundary conditions for the AI tool to phrase also the problem in the correct way, then you will probably get really good results. Yeah. Okay, so now since we want to create an app on accelerated lifetime modeling, I just refresh a little bit what is the theory behind it, and I also list some pitfalls that you might have encountered when dealing with this classical topic for reliability engineering, right? So in order to do that, I always present this really easy example. So you have a chicken that is on the skewer, you have fire behind, below it, and the function. So if you focus on the skewer, we want that the skewer sustains the chicken so that it doesn't get burned. Okay, so the function of the skewer is to avoid the chicken gets in contact with fire. Okay, this is the function definition. So we can model the skewer as a beam. That's a classical theory. So beam of length L, where force is applied on one of the extremities. And this is, let's say, the input, the mass of the chicken, and the output is the displacement that the skewer, the vertical displacement that the skewer is doing. So we can connect according to a really basic approach. We can connect intended input, which is a force, with intended output, which is displacement, and we can put them in relationship with a Cartesian diagram, and we will see that, of course, the relationship is linear. We should not forget also what are the unintended inputs, so what are all the conditions the skewer is expected to operate in, like the temperature in this case, and we do not have any unintended output like side effect, like some for a gear, like wear, noise, particles, something like that. Is coming from the function, but this is not desired, let's say. But just focusing on the horizontal axis, we can put intended input, intended output together. So basically, if we connect the y with the x, so the output is displacement, the x is the force on the extremity, and what is say the parameter is defining the behavior, and is 1 over k, which is 1 over stiffness. Okay, that's pretty straightforward, but that is really important because when you're going to do accelerated lifetime modeling, the first point you need to take into consideration is what is the parameter that we are going to monitor and is expected to degrade. And this parameter is, the relevant parameters is that parameter impacting the function. In this case, when we want to investigate behavior degradation, we just put the k, so the stiffness on the y-axis, and we look over time whether this is degrading over time, right? And this is how we should proceed for degradation. I'm saying that because otherwise, I've seen a lot of times people that are taking parameters or monitoring parameters that currently they are not impacting the function. Yeah, but so this is the way to do that is first we define the function. From the function we define the behavior. The behavior can be described by a parameter, and this is of course the easy case, and then we look at the degradation of that. Okay, and then what is the classical approach to accelerated lifetime modeling? Basically, you derive the degradation course at different temperature. T1 is greater than T2, that is higher than T3. And of course, the higher the temperature, the shorter the time to failure will be. And you get this tree course. And then plotting this point in terms of logarithms of time to failure, which is here indicated because it's where I've defined here the threshold. Yeah, so T1 is for the shortest one, over 1 over temperature. If the points so are lying on a straight line in a semi-logarithmic diagrams, because we have log here on the time and we have 1 over temperature, the x-axis. So if they lie on the straight line, the slope, it turns out that the slope is the activation factor divided by the k with Boltzmann constant. Therefore, the activation energy is determining the slope of the Arrhenius curve. So if they stay in the straight line, so we can apply Arrhenius. Okay, so basically this is pretty easy, but the Arrhenius model is well known, and I think in all the companies is requested, is always related to degradation mechanism or time activated degradation mechanism. But the advantage of this Arrhenius model is that, of course, you can set whatever temperature you want, and you can get what is the equivalent time to failure. Okay, and from that, you can calculate the activation, the acceleration factor, which is always requested by company which do not, which have neither time nor money, and they want to accelerate their test, and you get it, the TUs, to the T in the time in the field divided by time by testing, you get this acceleration factor, which is the result of this equation. Okay, this is pretty straightforward. Okay, but applying Arrhenius it might be really straightforward, but it contains a lot of pitfalls, right? So, and there is not just so Arrhenius is the most famous accelerated lifetime model, but there are many others. I just mentioned some of them. This is Cafe mentioned. Instead of exponential law, we have a power law here, and we have Albert-Peck, which is a combination of a power law and exponential. An exponential law, which is combining humidity with temperature. So these mechanisms, all these models are related to different damage mechanisms and stress factor. For example, Arrhenius is related to thermal aging, and the stress factor is the temperature, long time exposure to temperature. That is well known, but in the reality, what we are doing is doing degradation curves and try to fit, as I told you before, in order to see whether the points really lie properly on a straight line. Okay. So this is a typical approach that is used for accelerating test. Yeah, and as I said, a lot of pitfalls are hidden. Yeah, and we're going to briefly to look at the different pitfalls that we might encounter. Typical pitfalls are summarized here in this table. So there are general approach risk, like generally asking for acceleration. So every managers want to save time and money by accelerating tests, right? Or asking for activation energy. There are some pitfalls related to degradation curve, and there are some pitfalls related to accelerated lifetime modeling. So this using of these models. So we just review them, looking at pitfall number 1, generally asking for testing acceleration. So basically, there is product manager, reliability engineer, and the product manager ask to accelerate testing results, and the newbie reliability engineer has no time to do any test, no resources, just accelerate. Yeah. And this is okay. The question is, of course, not well posed, but looking at any document, for example, these AC, if you look at in a naive way, you will find some acceleration model here, right? Yeah, but of course, you need to know if this damage mechanism really represent if the acceleration if this acceleration model really represent the damage mechanisms that are ongoing, right? Because I've seen a lot of time applying Arrhenius in any case just to accelerate whatever test it has to be done. Okay, so first of all, as reliability engineer, we need to be focused on damage mechanism and then derive what is the best model and not the other way around. The second question, is also really risky. In this case, product manager is asking for activation energy. So I know the damage mechanism, I need the activation energy, right? But as you know, activation energy depends strictly on the damage mechanism itself and the material, the design, and the process the part is made with. And even in this case, looking in the literature might be really risky. Because if you see here, take into account always the same document, you see the activation energy is 0.7 electron volt, which is pretty famous, right? But in this case, the procedure is also saying that it might range from minus 0.2 to 1.4 electron volt, which is completely, is a huge range. So if you look, for example, activation factor that I showed before, and we plot it on the y-axis as function of testing temperature, changing, if we look at 340 degree Kelvin, and we look the impact of activation energy, we see that the acceleration factor is like 11 if the activation energy is 0.5, but it can explode to over 80, if the activation energy is 0.9, okay? So saying that the activation energy might change between minus 0.2 to 1.4, it means you can cheat with your data as you want, in order to make your manager really happy. But in reality, you are not representing the reality, and it's pretty risky. Okay. Then we move to pitfall number 3, which is related to the function analysis I showed before. So not monitoring the right degradation parameter. So for example, here I took an optocoupler, which is an electronic component. And if you look the intended, if you do the same story as before, so we try to connect to put in relationship intended input, which is a forward current, with intended output, which is collector current. Turns out that you have the CTR, the current transfer ratio, which is the relevant parameter, and therefore the CTR is the parameter that has to be analyzed when doing degradation analysis. Okay, so it's coming from the functional analysis. Yeah. Moreover, the degradation is not necessarily monotonely decreasing. So for the capacitor, you might want to look at the capacitance, which is decreasing, but the equivalence resistance is instead increasing over time. Yeah. And not all properties are affected by degradation in the same manner. Yeah, this is an example for plastic material. This is, say, a really schematic and example, but if you look at some data sheet, you will see the same trends. If you look at, for example, tensile modulus, and if you look how the tensile modulus degrades of a plastic material over time, exposed to a certain temperature, you will see it remains pretty constant because it's the global properties of the material. Instead, the impact strength will decrease a lot and is much more sensitive because it's a local properties of the material, especially for notch impact strength, right? So if the impact strength is the material property that hurts you, then you should consider it. If it's like you are designing just according to stiffness, then the tensile modulus is important, and the impact strength, degradation of impact strength might not be so relevant. Okay. We now move to pitfall number 4, extrapolating the degradation curve far beyond tested range. So what happened generally is the degradation curve in the literature or the theoretical degradation curve are really nice, but in reality, what happened is that after 1,000 hours, 2,000, 3,000 hours, you get a degradation of your parameter by couple of percentage points, right? So you get from 100 to 95, 98, yeah. But your criterion is like 50. So when you say, okay, I have data, I have the data in virgin state, and then I have a 99, after 1,000 hour, I have 98%, 95%, and then I extrapolate trying to fitting. Yeah, but this is like magic, right? It's not like really scientific approach. There are some norms that are suggesting to extrapolate up to 6 times of the tested duration. Yeah, but since you need some results, you are forced, right, to at least estimate what is the time at which the threshold value is exceeded, right? So in this case, as engineers, we need to always take some conservative assumption, yeah. But what I'm trying to say is that when you see a range analysis or whatever acceleration lifetime analysis, you should always take into consideration, or let's say question at least, how the degradation curves have been derived. So these are examples from literature. You see here degradation of a LED at different condition, temperature, humidity, and you see that the analysis was done up to 2,000 hours, and the degradation was like maximum 8 points in really harsh conditions, like 95 degrees, 95% relative humidity, which is the highest or the harshest condition you might have. Yeah. So, but the point is, you do not have so much time, you do not so much money to do that. So, it's quite a common challenge. And this is another example. You see, it gets to 1,000 hours up to 3,000 hours, but it's always the same thing. Pitfall number 5: assuming degradation low from the beginning. So this is always from the paper. Here you see the link. And you see here, that you might in this case the author has tried to derive some linear fitting for getting degradation curves, and you then plotting, as I showed before, you can generate the Arrhenius curve. But if you change the model, the Arrhenius curve change completely. Okay, so even in this case, it's the data that you have, they are probably not sufficient to take any good statement, and therefore you need to take conservative assumption or get more data. Okay, great. So these are other typical aspects for refrigerator. You have here other type of degradation curve that you might want to consider, and if you want to look at the resource, here is linked on the bottom of the slide. Pitfall number 6: use wrong failure distribution shape. So this is possible to do, for example, with some software, commercial software. Basically, what we generally mess up variable with exponential distribution. So the fitting curves are following an exponential degradation in many cases, yeah. But if you look at the distribution, yeah, at certain stress level, this will be like a variable or log normal distribution in most of the cases, yeah. Because this is what we call the wear out damage mechanism. So the longer the time, the higher the probability of getting worse will be. So it's typical wear out mechanism. Yeah. In the software, you can also choose an exponential distribution. Yeah. For the data. So you use exponential degradation course and exponential failure distribution, which is wrong, because you are assuming that these data points arrange according constant failure rate, which is basically not physically possible. Just remind you the bottom curve. So the bottom curve. So if you look at aging and a range or acceleration model are dealing with wear out mechanisms. So the failure rate, the mortality is increasing. Okay, so we expect this kind of failure distribution. Okay, pitfall number 7, which is pretty famous. So you generate an acceleration factor basically only based on temperature, and you see, okay, the acceleration factor is not so high. I need to accelerate more. Then you consider another factor. You consider humidity, even if the humidity is not relevant at all. Okay. So you say, okay, I multiply this factor by this factor. In this case, I can accelerate even more. Yeah, this is practically wrong, because if the humidity is not triggering your damage mechanism, basically you should not include it in any acceleration factor. Yeah. Of course, the higher the number of factors you consider, the shorter the equivalent time testing time will be. But if the humidity plays no role inside your damage in the damage mechanism, then you should not consider it. Pitfall number 8, I think, is the last one. So okay, so it's basically is not the right presentation, because I had some problems before. What I'm saying is that, yeah, imagine the case you have a cake in the oven. Yeah, you might want to reduce the time to cooking it by by increasing the temperature. You might do that until you get a certain limit. After that, if you exceed the limit, you burn the cake. Okay, so that's definitely the case you should not do. So the analogy, baking a cake in the oven is the same as doing a test. So you should not overload the sample, because otherwise you might activate different damage mechanisms. Okay, so this was the list of pitfalls that we can encounter when doing accelerated lifetime modeling. I just mentioned 8 of them. Probably there are some many more. But this is something we should take into consideration when doing accelerated lifetime modeling. Now, being aware of what can happen, we are going to do the following. We are going to do a web app. A web app for accelerated lifetime modeling using ChatGPT, PyCharm, which is an ambient for Python, and Streamlit. Okay. So now I need to move to share my entire screen. Yeah. Okay. So you see now, you see my the ChatGPT environment. So we want to start a fresh conversation, because ChatGPT knows me. Yeah. So basically knows all the prerequisite I set when doing an app, and I've been doing apps for a long time. So it basically it provides a better solution than what I expect. So I'm trying to do now a fresh conversation. So I write, let's start a fresh conversation. Make as you don't know me. Okay. And so in this case, yeah. So now we say, okay, let's create an app able to fit degradation course from synthetic data. So we create a data set, or we let ChatGPT create a synthetic data set. Let's create an app able to fit degradation data and derive from them an Arrhenius plot. Okay. Degradation starts from 100% and a failure criterion is reached at 50%. Okay. This is like, let's say, a really naive prompt. I want to complete it by saying create a Streamlit app, and then I say, okay, please provide the full code. Okay. You can do also by yourself if you want. Able to feed the gradation curve from static data and derive from them a Arrhenius plot. Okay. Let's see what happened. So is start creating. So probably I'm not sure that he has forgot everything about myself, because for example, you see here he is going to build an Arrhenius plot in terms of logarithm of time to failure versus 1/t. Basically, in the previous attempts I made, it was providing, so for example, versus temperatures, not 1/temperature. So I think it's already improved. Yeah. And moreover, in the previous version, he hasn't provided any activation energy in terms of electron volt. But you see, so he has already finished. So this is the code. Okay, this is pretty much the code. So he's importing the packages, then is configuring the app, that's including the constants, then is defining the model functions, which are these def. Okay. Then is included the sidebar controls. We're going to see what it means. Generate and analyze data, then use temperature prediction and summary metrics. Degradation curve plot, Arrhenius plot, results table, synthetic data table and downloads, model explanation. Okay, so you see it's pretty rich. Yeah, let's see if how it works. So now I copy it, and so I open it here in PyCharm. I call it demo 1. Okay. You need, of course, to download PyCharm or whatever Visual Studio, and download afterwards also all the Python models. Then, basically, no, it's not copying properly. Why is not copying properly? Okay, now it has copied everything, and now you say, okay, let's run demo 1.py. Okay. So it's doing something. Let's see. Okay. Yeah. So what you see here is an app. Degradation curve fitting Arrhenius analysis. Let's see if everything is plausible. Then we start from the left. We have different testing temperature. We have true activation energy, which is in this case given as kilojoule over mole. Generally, we use electron volt. Then we have a reference temperature. Then we have true T50 at reference temperature, so 1000 hour at 80 degrees. Failure criterion, measurements per temperature, we can increase or decrease. Okay. The test duration as fraction of true T50. In this case, I don't know. Okay, so multiplying the testing duration as a fraction of T50. So you say, okay, it's 1.5 times 1000. 1.6, sorry. But we can ask what does it mean? And measurement noise, this is saying how the scattered data we have. Now we can play with that. And we are random seed and use temperature live prediction. Okay. So you see these are degradation curves, synthetic data sets. So we don't see here the data sets. I don't see that. And then we see the Arrhenius curve. Okay. So this is the example. Okay. So the Arrhenius curve is plotted correctly, inverse absolute temperature, 1 over temperature over logarithm of time to failure. Okay. So we can do some changes. For example, we can say enrich the app providing or making the data set visible. And we can say provide the activation energy in electron volt, EV. And then we can say divide degradation curves and Arrhenius model in tabs. Okay, so instead of having everything after, so the degradation curve and the Arrhenius lifetime plot in the same page, I'm going to have them on different tabs. What we can also do is use Plotly Express for visualization. This is Matplotlib is a different module, and Plotly Express is a different one. Okay. Okay, curve fitting results are there. Okay, let's see. And then say what happened. And is providing the whole code. So, I mean, I think it's really powerful. So despite these are, of course, naive prompts, what I'm doing right now, but it's really powerful because if you want to show an example of reliability approach, in the past, you started creating some Excel templates, and then it's quite a lot of time doing that. And in this case, you are just with a couple of prompts, you create some some really effective examples. Okay, I would say that beyond that, if you want to develop apps for your company, that might that becomes really powerful, but you need to structure a little bit differently. Not we start with naive prompts, but structuring the app in order to fulfill all the requirements that you have. Yeah, but basically there is no limit. Yeah. So now he has finished and we can copy it, demo one, and we can stop it, the previous app, Control C, and then say, okay, run it again. And then it's doing. Okay. So we see. Okay, so here you see it has changed the visualization. Here is not matplotlib anymore. So we have created some tabs, degradation curves, Arrhenius model is here. The data set is here. I don't know. So the activation energy is 0.78 is correct, right? And then you have full access. In this case, the order is not correct. It would say a data set, then degradation curve, then Arrhenius, but okay. Then if you have something that you do not know, because you can also consider the fact that you are new to reliability engineering, and you don't want to use this AI tool for provide relevant results for your company, but you want to explore a method. Okay, so you can start with naive prompts and then start conversating. And you get even more complicated app, and you can ask, for example, what is the measurement? What does it mean measurement per temperature? Why have you included test duration as a fraction of true T15? This kind of things, right? And you start the conversation. It takes some time, so that you learn a lot, and you can also challenge. Okay, you can also challenge the AI tool. What we can do as last step, we can say, okay, now please extend the app to Albert Peck and Coffin Manson. Be aware that these accelerated lifetime models refer to different damage mechanism. And yeah, and then we can say, and please store the results in terms of equivalent time for given load condition into a table, a dedicated table. Okay. Okay, so and say, okay, let's do accelerated lifetime model, but not just Arrhenius. We want to do also Albert Peck and Coffee Manson. And okay. It was searching on the chain reliability, Fred. Oh, is looking at different. Okay. In the meanwhile, what I can. Let's stay here for a while. It's the app now is much more complicated. Is longer, and it might get to a critical point where you say, okay, divide the app in multiple files, each file is a tab, for example, or collect all the equation in a separate file. Yeah, you can do in a more structured way than what I'm doing right now. And moreover, you can ask also the AI tool to suggest some structure. Okay. Yeah. So it takes some time, but it should be almost finished. In the meanwhile, I can show you, for example, some other examples I have created. You can also host your app on Streamlit. This is free, but the app should be public. Yeah. But if you look, for example, I don't know, if you look at, you can do like best fit app. You you can do whatever fatigue analysis app. So these are, let's say, small breaks that you can use and you can share with your colleagues for analyzing the data. And of course, you can also create your virtual machine and share the results with your colleagues. Yeah. Okay, let's see here if it. Okay, here is. See, it's not finished, so we can copy again this file here. We can paste it. Say, okay, let's see what happened. Now you see you have, in this case, the solution that he proposed was like, okay, he has proposed different tab solution, Albert Pack here, temperature media degradation is also, for example, provided Albert Pack fitted lifetime surface. Yeah, where you have, what do you have here? You have, okay, you have temperature and relative humidity and predicted time to failure. You can coffee Manson, you have included here, and you have so the equivalent exposure here. You have, yeah, he has created in this case, you know, test temperature, 100-degree use temperature, 25-degree applied testing time. He has created here, yeah, the equivalent use time. Yeah. Yeah. Yeah, so it's not so nice. So he had I thought he was storing the data differently, but this is also a potential outcome that you have. And as soon as you get, let's say, more knowledgeable about app developing, you can so guide the AI tool, and setting the boundary condition, yeah, so to have the app you were expecting. Yeah. So yeah, this was the other app I wanted to show. This is, for example, a best fit probability distribution app. You can upload here the data, or you can paste the data here, and then you get the best fitting tools like that. Okay, so this is anything, yeah, really, really, it's really basic, yeah. But you can compare different distribution, and generally for doing that, if you do that in Excel, it takes some time. So you have other tools like, I don't know, ReliaSoft or Minitab or whatever you have. Yeah. But there are a lot of companies that do not have these tools, or where people they need some basic tool to advance in their analysis, and instead of creating by themselves, in Excel and then share in the organization, you can create this kind of easy dashboard, and you can then share with your colleagues and enrich them as you want. Okay. So this was the creation of the strategy lifetime and equivalent exposure analysis. Okay, this is just a first attempt, but you will have a lot of fun doing that. If we move then to the presentation again. Okay, so I showed briefly and naive way how to create
Enrico,
lifetime modeling.
Enrico, we got one question here.
Yeah, please.
So it's from Yogesh. How ALM can be applied to PCB and PCBA components, since degradation is different for active and passive components during operation?
Yeah, that's a great question. So, assuming you have a board, you have like temperature sensitive components, and you have some electromechanical components. And the damage mechanism might be different from LED is lumen maintenance. For IGBT is power cycling, for example. I mean, that is something that you can solve by generally some clustering-based approach, including what are the most damaging configuration and condition for different components. Okay, so if you apply, say, if you apply just temperature-induced load, so the board is exposed to a certain temperature over a certain time, then you're going to trigger just damage mechanisms for LED. Instead, if you apply power cycling, you are just damaging IGBT. So what you can do is to identify what is the worst case condition across all the maneuvers or configuration you have in your product, yeah, to create an envelope able then to test, to be used as testing procedure for the board. So you cannot go component by component. This is not a procedure I would follow, but you should consider an envelope that is taking the worst from different damage mechanisms.
But you're really focusing on what's the damage mechanisms and what's the relevant environments that would excite those, would encourage them to happen. And he also asked about optical components, and that, again, it's really what are the salient damage mechanisms that are going to occur in your application, and then what's the environmental conditions that then would accelerate those things or cause them to occur. And that doesn't change whether you're doing AI assisted or not. You got to think at that level to be able to model these things.
Yeah. Can I go ahead, Fred, or is there any additional question?
No, good. You're good.
No, I mean, I've come to the conclusion here. So what I was showing you is that generative AI accelerates learning by providing explanation, examples, and you can compare different configuration, which is really powerful, to my opinion. So we are supporting also the theory that we learn in the books with AI tools that can create scenarios, yeah, and they can immediately create some dynamic apps. I would say so. Python is really powerful because it enables engineers to convert this theoretical knowledge into code and streamlit. But there are some other providers, they make it interactive. There's also Dash, There is also, you can create an HTML, but you create it interactive and you can play with different scenarios. Yeah, of course, you need a solid reliability background. Therefore, I went through some of relevant pitfalls that you might encounter when analyzing accelerating lifetime modeling. And that's helped you for correctly interpretation of the output, which might be pretty dangerous. So my warm suggestion is to challenge the assumption, to challenge the AI and to challenge AI generated results. Because for example, as I showed before, the degradation curve was up to 10,000 hours. How did you derive the degradation curves? Right? This is a typical question. And then you see if they are like synthetic, it makes no sense to get to analyze the outputs or to treat the outputs seriously. So the engineer remains responsible for defining the problem, providing valid data, checking the code, and validating the conclusion. So you are, let's say, the orchestrator, the one who provides the data, and you get supported by AI. And I think it's boosting your productivity a lot, but you remain the core of engineering, and you know why if AI has deliver proper results or not. Thank you for your attention. If you have any question, I'm happy for answering them. Thank you also, Fred, for giving me the opportunity of hosting this webinar today.